Okay. So, welcome to the tutorial number 12 on aircraft propulsion. Today, we will be dealing with the uh, axial turbines. So, as you can see in this figure, this this is what axial turbine looks like. This is a rotor. This is a rotor uh, of a gas turbine, and you can see the particular shape of the airfoil that is being used in a gas turbine engine. So this is how the gas turbine uh, blade looks like. And also one thing is to be uh, notice is the blade profile varies along the height also. So along the height, the blade profile may vary or may not vary. It depends on how you have designed your turbine turbine blades. So so you might have studied in the lecture by Professor Kulkarni that there is something known as free vortex design, right? And for a free vortex design, the tangential velocity, the product of tangential velocity and the radius being from the center to this point, at any point on the blade tip is constant, right? So this is one of the design that is being used in a gas turbine uh, blades. So yeah, so this is how a blade turbine looks like, and how they are made is they are fabricated in a single piece, and they are assembled onto a rim. So this is a rim, huh? And they are assembled onto a rim like this. So okay, so so in between these two stages, these are the stages. This is first stage, this is second stage, this is third stage, and so on. So in between these stages, we have what is known as uh, the the nozzle that is kept in between these stages. Okay, so right. So let us look into the velocity triangle for this turbine blade system. So first stage, first is your nozzle. This comprises of your turbine stage, and first part is the nozzle, and other is a rotor, as demonstrated in the image. Uh, so yeah, so okay, so you have the tangent to this blade, and that makes the angle. Uh, yeah, makes an angle alpha 2 with the blade. So this is and the rotor blade moves with a velocity u. So the relative velocity is v, and absolute velocity is c2. This is v2. Uh, okay. So if you see this diagram, you can make a velocity triangle as shown in this figure. Okay. Okay. So yeah. So you can make a velocity triangle like this, and similarly at the exit also you can create a velocity diagram as shown in this figure. So you can combine these two diagrams and to get a what is known as coupled velocity triangle. Uh, so yeah, because your velocity u is constant for the uh, f- for the inlet and the outlet. And this is to be mentioned. It is to be noted that this thing is made at a particular radius. This is at a particular radius. So your velocity, the the profile of the blade might vary along with the radius also. So generally what we do is we study the velocity triangle at a mean tip radius. Mean blade radius. So what does it mean? So mean blade radius is somewhere somewhere in between these blades, right? So this is your RM, what we known as RM. Okay, and this the bottom part is your root, and the top part is known as tip. Okay, yeah. So this is how a velocity triangle is formulated, and the the sum of tangent so these are the identities that is already being um, taken up by professor. So and this is your work done from the turbine. Okay, that depends on your axial velocity, your velocity at which the turbine is rotating, the rotor blade, the blade speed. This is the blade speed. This is your uh, axial velocity, and this is this, and other is the geometry of the blade. Okay, and also you have mass flow rate. This is your blade speed, and this is your axial velocity. Okay, and this should be equal to what, according to the thermodynamics, it should be equal to the rate of change of enthalpy from the uh, gases. Okay, so you if you see the velocity, the TS diagram for this is your T naught 2 and this is T naught 3. So this is how we have defined our efficiency for a particular stage. So if you combine these two diagram thing, you can calculate what is the temperature drop across each stage. Given what is the mass flow rate, the velocity at which the blades are moving, the axial velocity, and the geometry. If these things are fixed, you can always calculate what is the temperature drop across each stage. Okay. So next thing is the degree of reaction for a turbine. So this is the enthalpy drop across the stage, across the rotor, divided by the total enthalpy drop. When you solve this equation, you will get a relation in terms of the blade angle, as shown in this figure. So as shown in this figure, yeah. So okay. So this is the relation between the okay. Where is that? This is the relation between the the degree of reaction and the blade speed. So it depends only on your uh, yeah, this depends on a flow coefficient and your geometry. Again, the flow coefficient and beta, the blade angle depend, they also vary along with the radius. So lambda, the degree of reaction can also depend as a function of radius also. Okay, and now you have a blade loading coefficient, that is the work done divided by the normalized the uh, blade velocity. So if you do this, you'll get the relation for blade loading coefficient uh, as shown in this equation. Okay, so if you, and then you can always write your blade angles. So if you have to calculate what should be the blade angle for a particular blade loading coefficient, flow coefficient, and your degree of reaction, you can always calculate what should be a blade angle using this relation, tan beta 2 and tan beta 3. Okay, so right, so uh, right. Then you have your okay, free vortex design. For this, the product of tangential component and the radius should be constant. Uh, yeah, and then what else? Yeah, then okay, okay. Then let us come to this radial flow turbine. So in a radial, so can somebody tell me an example of a radial flow turbine? So any idea which turbine acts as a radial flow turbine? Or you can answer this thing as a mixed flow turbine. Okay, so one thing is that Francis turbine is one of the example of a radial flow turbine where the flow comes from the volute. This is known as volute. It passes through the nozzle and then through the impeller. Okay, so yeah, Francis turbine is not a pure radial flow turbine. It is the mixed flow turbine because the in a Francis turbine the flow comes in a radial direction. This is the radial direction, and this is the axial direction. So it comes inside in a radial direction and goes outside in an axial direction. So this is a mixed flow turbine. So yeah, so you can have a radial flow turbine also. So velocity diagram is shown in this figure. So instead of this axial component, you have a radial component. Okay. So right. So this is some equations for these things. And okay, let us start with the assignment type problems. So okay. Uh, okay, let's have an open discussion to this. According to the velocity triangle of axial flow turbine, which of the following option is true? So, okay, somebody can answer this question for me. So, so which of the following is true? So the relative velocity. Okay, let us make a, PS diagram. No, the velocity diagram for this, and let us try to answer these questions. So this is your velocity triangle, coupled velocity triangle for axial flow turbine. So this is your C1, this is your C2, this is your okay. This is your C2, this is your V2, and this is your alpha 2, this is your beta 2. Okay, and you this is your C3, this is your V3, and this is your this is your beta 3, and this is your alpha 3, right? So let us answer this question. Relative velocity and axial velocity component at the outlet are higher than the inlet. So is it true? The axial velocity does it change from inlet to outlet?
No.
Okay, so this cannot be the answer. So the relative velocity component at the outlet is lower than the inlet. So so the relative velocity component is this V3. So if this triangle, uh, does it looks like that V3 is smaller than V2 by the magnitude wise?
No.
No. So this cannot be your answer. The whirl velocity, uh, okay, the absolute velocity component at the outlet is lower than the absolute velocity component at the outlet is lower than the inlet. So absolute velocity is this C3. So is C3 is less than C2,
Yes.
right? So this could be the answer, but the second part is the blade speed remains constant. So the blade speed U remains constant. Is it true?
Yes.
Okay. So okay, then the correct answer is this. Let us look into the fourth option also. The world component remains constant. So the world component is this CW2, and this is CW3, right? So will it remains constant? No. So the correct answer is C. Okay. So let us
I'll update to the team.
okay. So let's come on to the second problem. Uh, for 90-degree inward flow radial turbine, which of the following is correct for the velocity triangle? So let us make a velocity triangle once again for IFR. So it looks like this. This is at your inlet. This is at your outlet. And if you okay, so when you make this is C2. Okay, 1 minute. This is your C. This is C2, and this is CR2.
Sir, world velocity is equal to the radial velocity.
Okay, which one?
Uh, I don't know the second part, but I don't know. I know the first part. That radial is equals to the sorry world velocity.
Okay. Right. So let us look into the velocity triangle. Maybe we can answer this thing. So this is yeah. 1 minute. This should be two, and this should be V2. This is CR2, which is equal CR3, which is equal to C3, and this is U2, right? So let us see this. See, okay, this is one actually. They have mentioned as one. So let us assume that two is one and one is two is three, right? Two is three. Okay, so this is two. So CR1 is equal to CW1. Is it so? No, right? They both are different. So U1 is equal to V1. So U and V doesn't have any relation. So this is wrong. So CR1 is equal to C1. CR1 is equal to C1. No, that is not true. The CR1 should be equal to the relative velocity, right? So this is wrong. So then CR1 is greater than CW1. CR1 is greater than CW1. Can we say always say this? Is it true? Can we always say no? Right? It depends on the angle, right? So let us see. CR1 is equal to V1, which is true, and U1 is equal to CW1, right? So this is your correct answer. Okay. So okay, let us see this. I hope you can see the problems now. Yeah. So, in the case of axial flow turbine, blade loading coefficient is a function of. So, blade coefficient uh, for axial flow turbine is given as. So, how do you define a blade loading coefficient? So, this is a work done by half
U square. Work of
u
U
square,
square.
right? So, what is the work done for this? So, this is if you substitute, you get okay. This is work done per unit mass, right? So you have u CA, then you have tan beta 2 plus tan beta 3, right? Divided by half u square. Okay. So if you substitute this thing, you will get as u cancels off and you get 2 CA by u is 5, right? So tan beta 2 plus tan beta 3. So let us answer this question. So in case of a axial flow turbine, blade loading coefficient is a function of, so whirl velocity component, does it appear anywhere? No, right? So axial velocity, no. Okay. So it is only a function of flow coefficient and a blade angles. Okay. So this is a correct answer for this. And work done factor, whether it comes to this, no, right? So this cannot be the answer and not the velocities. So the correct answer is C, flow coefficient and the blade angles. Okay. So okay. So can you answer this problem again? So in case of a 90 degree IFR, uh, the degree of reaction is a function of lambda. So they're asking for lambda. So so what, how do you define a, lambda for IFR? Okay, so this is given by this relation, the relation here. Okay, so now I hope I, okay. So the lambda is this, right? So now can you answer the question? So it depends on your. So this is a blade velocity. This is your whirl velocity, and this is your relative velocity. Okay. So which answer matches these? So blade velocity, not the absolute velocity. Blade velocity, whirl velocity, and relative velocity. So the correct answer for this is uh, B. Okay. So so okay. Can you please answer the this question? For axial flow turbine, the absolute velocity, uh, it increases, decreases, or remains constant from inlet to outlet of the rotor. So how will you go ahead for this problem?
By seeing the velocity triangle.
Exactly. So by looking into the velocity triangles. So this is a velocity triangle. So how does a axial flow turbine absolute velocity? We have to compare inlet and outlet. So this is which is your absolute velocity in here?
C2 and C3.
C2 and C3. So C2 is greater than C3, right?
Yes.
So the at the outlet, the absolute velocity decreases as compared to the inlet. So for inlet, the absolute velocity decreases from inlet to outlet, right? So the correct answer is decreases. Okay. Uh, so let us move to the other problem. For the inlet velocity triangle of 90 degrees, inward flow radial turbine, the whirl velocity component is equal to. So how will you proceed for this? Uh, so this is actually similar to the previous problem. Uh, this problem. Uh, okay. The whirl velocity component they are asking. Okay. At the inlet. So at the inlet, the whirl velocity component is equal to the blade velocity, right? So the correct answer for this is the blade speed. Okay. So okay. Coming on to this problem, which of the following is correct for the flow through a 90-degree inlet radial turbine? So we have to tell from where to which location the flow takes place, which is the correct order. So can you please answer me? So for this,
First, it should flow through the nozzle ring,
nozzle,
volute, nozzle
volute,
ring,
yes,
impeller, exhaust diffuser.
exactly. So what you have is you have a volute, then followed by the nozzle, then followed by the impeller, then you have your exhaust, right? So which is the correct answer for this? That is the B, inlet volute, then inward volute, impeller. Okay, not this, right?
Yeah.
Which is the one?
Answer A.
A, inward, nozzle, ring, impeller, and the exhaust. Yeah, you're right. Correct. So let us look into other problem. So for 90-degree inward flow radial turbine, again for this, um, the flow through the nozzle leads to. So okay, um so we are asking at this point and at this point. Okay. So what happens across a nozzle? So this is something similar to this what we read in the nozzle. So you can assume there is a nozzle. So you need not to remember about this turbine itself. So it's just a nozzle. So what happens across the nozzle? So does the total temperature increases,
No. No.
right? What happens across a nozzle to the total temperature?
It's constant.
It remains constant, exactly. Okay, it remains constant. Okay, then increase in total pressure,
No, it should drop.
it should drop, right? P naught should decrease. Decrease in total pressure, yes.
Yes.
uh, Constant total pressure, no, right? Because there is always friction losses. Okay, there are losses that contributes to this.
Uh,
So
One question here.
huh,
In the lecture by the professor,
huh,
in the HS diagram, it was shown that even across the nozzle,
huh.
the enthalpy drops. So in that case, temperature also drops, right?
Yes, yes. So okay, that actually that happens. Okay, when we say this, we assume that there is no heat loss from the nozzle. Okay, there is assumption that is inherently that is being used, but sometimes we do not write this. But when in an actual nozzle, what happens? There is always heat loss, right? So to the outer parts. So there will be the total there will be decrease in total temperature. If there has been option for this decrease in total temperature, it could be the uh, possible answer for this. Okay.
Okay.
Uh, So okay, let us look into some numerical problem now. So what we have is uh, okay, we have a single stage axial turbine with a free vortex. So immediately, what should we have it in our mind? So after looking into these two data, anything that we should first think about is okay. So whenever we have a problem related to the turbo machinery, so best practice is to make a velocity triangle now, and a field vortex is something that the tangential velocity and the radial distance remains constant, right? So let us make a neat diagram. Okay. Okay, sorry. Okay, so let us start naming it. This is U. This is yeah. Okay. arrow should be in that direction. This is C2. This is V2, and this is this is C3, and this is V3. This is our axial direction. Axial direction. So this component is your CA. This is again your CA that remains constant. Now what we have is right the angles now. So this is your alpha 2, this is your beta 2, this is alpha 3, your beta 3, right? So now let us see what all things are given up. So okay, and also we have nozzle and nozzle stage, and we have your rotor stage. Okay, so this is a stage one, this is a stage two, and this is a stage three, right? So total now the total pressure is given. That is that is a 6.5 bar P naught at this location, and total temperature is given. T naught is 900 Kelvin. Mass flow rate is given. This is a 930 kg per second, and yeah, your static pressure is given at this location. Pressure is given at 1.7 bar. Okay, and okay, mean blade height diameter. Blade mean diameter to the height ratio is given. So how does it relate to? So this is your blade height, which is h, some h, and that is connected to a axis. So this is from here till here. It is dm. Okay. So there's a mean height given, and the ratio of these quantities given. H by P is given as 1 upon 15. Okay. So nozzle efficiency is given. Nozzle efficiency is the efficiency of stage 1 to 2, the station 1 to 2, and nozzle outlet angle is given. So nozzle outlet angle is your alpha 2, that is the 65 degrees. Okay, this is given. Then what else is given? CP and gamma is given, and we are required to find what is the blade mean blade diameter of the rotor. So how will you proceed ahead? Any idea how to go ahead with this? How to calculate the mean blade diameter? So okay, so let us assume this now, that we have this information, and also we have what is the mass flow rate. Okay, so if I assume that okay, um, not this. So if I assume that uh, this this is how it looks like. So in this region, the flow will take place, right? Let me not make it. So yeah, so it will be something like this. Okay. So this is a dime. This is your RM actually. This is your RM, and this is your H, right? So okay. So now what we have to do is we have to find what is the mean bleed height. So one thing that we know is what is the mass flow rate that is going through this cross section area, right? That is being swept by the blades. So, and the mass flow rate through this is given m dot. Okay. So how do you calculate the m dot from this? So part one, that is a m dot, right? So m dot is, how do you compute your m dot? That is the rho a v. So what will be the velocity for this? Okay, what rho will you take for this? This is your rotor section, right? So what row will you take for this? So that should be at session 2, right? So the information is given for 2. Whatever the mass flow rate that is going through this, through this should is equal to the mass flow rate that is going through this, right? So density should be taken at 2. What is the area that is what is the area of this cross section? This cross section, how do you calculate the area? This is just 2 pi r dr, right? And yeah, and what is your what should be the velocity for this? Which velocity will you take? So which component of the velocity will you take? So this is your axis, right? So which velocity component will you take? And this is rotating in this direction, say omega. So okay, so can you answer me? Which velocity are we talking about in this rho AB question? Okay, so it should be the axial velocity, that is a CA. That should be a CA, right? So now let us calculate what is each and every. Okay, another thing. If you see this area here, that is rho 2 pi Rn. It is just a diameter dm, and t- uh, we are we are looking into the we are looking at mean diameter. Okay, we are looking at mean diameter, and this is how the profile looks like at the mean diameter. It might change along the radius also. So this is, and dr is just the blade height. Okay, and this is ca. So right. So how will you get the angle is known 65 degrees, but how will you calculate ca for this? Any idea? How will you calculate what is ca for this? Okay, so okay, so what we know is about what the information that we know about nozzle. We know the velocity exiting this nozzle should be equal to the C2, right? And how do you calculate the C2? You can calculate using the efficiency of the nozzle and the parameters that is given here. So right. So if you take the efficiency of the nozzle, it is this T naught 1 minus T2 by T naught 1 minus T2 dash, where this is our T naught 1, this is T2 dash, this is T2. Okay, so T naught 1 Okay, this is 1 minus T2 by T naught 1, 1 minus T2 dash by T naught 1, efficiency of the nozzle. So 1 minus T2 by T naught 1, 1 minus P2 dash by P naught 1, gamma minus 1 by gamma efficiency of the nozzle. So from here you can calculate what is T2. So if you calculate T2, where is given as 95% and P2 is given as 1.7 bar, and T2 is T2 is 6. Okay, and you know what is T naught 1? This is 900 Kelvin. Okay, so I and P naught 1 is also given, that is 6.5 bar. Okay, so also gamma is given as 1.33. If you substitute all those parameters in this equation, you will get T2 as 657.9779 Kelvin. Okay. Now from here you can calculate what is your velocity. So this is your nozzle. So this is a nozzle. This H naught should remain same across the inlet and the outlet. This is 1. This is 2. This is H naught should be equal to H2 plus C2 square by 2. Okay. So H naught is T naught, that is 900. So 900 minus 657.9779 into 2 into CP is 1.147 into 10 to the power 3 to the power under root. This is a C2. So if you calculate C2, you will get around 719 point. Okay, you will get 745 something. Yes, you will get as 745.1164 meter per second. Okay, so now you have C2. This is 745.1164. Okay, so now you can calculate what is CA2. CA2 is just C2 cos alpha 1. So this is 719.7271 meter per second. Okay, so CA is 719.7271 meter per second. Uh, okay. So now you have velocity, you have temperature. So you can calculate what is density. Density at 2 is your that is given as um, P2 by RT2. Okay. Now R is not given, so you can calculate using your this is by kinetic theory of gases. So and also using ideal gas assumption. Yeah. So this is your 1.33 and this is 1.147. So if you calculate R, you will get as 284.59 joule per kg Kelvin. Okay, so this is 1.7 into 10 to the power 5 by 287.59. T2 is T2 is 657.9779. So you will get density as 0.9078 kg per meter cube. Okay, so from here you get what is density. Now you can calculate mass flow rate, that is already given, that is 30 kg per second. This is your rho 2 um, pi d h uh, pi d h and your vf, right? So yeah, so, vf is just ca. Okay, So if you calculate what is your okay, now you can you know this is dm square h by d, and again this is ca. This is 30 kgs per second. So now you if you substitute this values 9078 pi, then you have d by h is 15. Okay, and this is dm square, and the velocity is 719.7271. Okay, and this is 30. So you can calculate what is dm. So if you calculate dm from here, so yeah, this is your you get around 7 8. So you'll get diameter of 688. Okay, there's 2 8 and 7 meters. Okay, I hope this is fine, right? So this is the main blade of a rotor. Then what is given is absolute velocity angle at the root of the rotor, at the root of the rotor. So let us calculate. Okay, let us first calculate what is the radius of the root and the tip of the rotor. So how to calculate it? This is this was your blade, and this is was your hub. Okay, this was your hub, and this was your uh, yeah. So these are axis, and this as dm, and also you know what is this h. So how will you calculate this distance? So how will you calculate this dt d root dr and this thing? How will you calculate? Okay, this is not this. This is rm, and so how will you calculate this? So this is just h by 2. This is also h by 2. Okay. So you can calculate what is rr. That is dm by 2 minus h by 2, right? So this is just dm by 2. If you take out common, you will get dm. So dm was 0.688 7 by 2, 1 minus 1 by 15. Okay. So by 2. So this is 0.3214 meters, and r is dm by 2 plus h by 2, which is your 16886. This is your 0.3672 meters. Okay, so we have calculated what is radius of the radius of the root and the tip of the rotor. Then what we have to calculate what is the absolute velocity angle. So absolute velocity angle is our alpha. So also uh, we know that, okay, what is the rm. Rm is your 0.6886 by 2. So this is 0.3443 meters. Now we know that for a, free vortex design, your tangential component is equal to C at the tip and R at the tip, and is equal to C at the root and radius of the root. Okay, so let us calculate what is CT and CM from here. So this is your okay. So let us calculate what is CM from here. So mm, CT, not CM. So this is CM is just 745.1664 into uh, into the sine component of 65, right? So this is a 675.304 meter per second. Okay, so yeah, this should be equal to this should be equal to 232.507. This is our meter square per second. Okay, the unit should be this. So divided by your answer divided by 0.3672. So this comes out to be 633.1901 meters per second divided by 0.32141. So this is um, 723.398 kilometer per second. Okay, this should be R, right? This is R. I hope you can hear me. Hello? Hello, can you
Yes,
hear me?
yes, yes.
Okay. Okay. So this is a velocity. Then your CA is fixed. That is your 745.1164 meter per second. So if you make a triangle, this is your alpha. Say, let me say that's alpha at the tip, and this is alpha at the root. So you have 745.1164 meters per second, and you have 633.1901 meter per second, and this is 723.3982 meter per second, and this is 745.1164. So alpha t and alpha r you can calculate. That is 745 633.1901 by 745.1164. Tan inverse answer is 40 0.3574 degrees, and alpha r is your 723.3982. Tan inverse of this is 44.1527 degrees. Okay, so this is how you calculate the blade angles and the tip. So how will you calculate what is the static temperature and at the root and the tip of the motor? How will you calculate? Okay, so now what you have is this is your C axial, C axle. This is a CW. A CW. This is your C2 at the tip. This is C2 at the root. The root. Okay. So with this, you can calculate what is this. Uh, uh, yeah. What is the CW2? That is just 74. This is some 977.817 4 meters per second, and CR2 is this is your 1038.5108 meters per second. Okay, so now we know that the stagnation temperature after the nozzle is constant at the tip and in the rotor. So you can calculate what is your this is some C2. Let us call it for tip. So T2 is 900 minus 977.8174 2 into 1147. So if you calculate this, so this is so this is okay, 900 minus 977.8174 by 2. So this is 899.573 uh, 5 Kelvin. And similarly, you can calculate what is T naught for this also, minus C2 at the tip by 2 CP. Okay, should be square, right? Yeah. Okay. 1 minute. So let me calculate it. So this is 900 minus 977.8174 square by 2 into 1147. Okay, this is then this is your the temperature is 483.20 Kelvin, and at this point you have 1038.5108. So square. So you at the tip you have 429.858 Kelvin. So right. So exactly. So this is your temperature profile. This is how you calculate the static temperature at the root of the rotor. So okay. So I hope this example gives you a clarity on how to compute different parameters for a axial flow turbine. So if you have any problem, please let me know. Any other problems? Any other doubt?
No, sir.
Okay. So let us close for the day. Okay. So thanks a lot.
Thank you, sir.